Hey guys, it is I, the Chili. Welcome back to Hardware 3D. In the last video, we got our omnidirectional shadow mapping all sexed up and it's good, but it's not great, right? And the one thing that I mentioned at the end of that video is this the self-shadowing here. You can see it, especially when you get the specular going on here. You can see these bands here. They're not super defined. They're not super jarring, but they exist. And you probably couldn't see them that well in the last video because I messed up the color space on the video. But if I don't mess it up in this one, you should be able to see these bands and you will know that we must do something about them. This cannot stand. And of course, the easy way to do it would just be to turn up our constant bias. But then we get the Peter Panning, which we obviously don't like either. So what I want to do is I want to do a little bit smarter stuff. I want to do like that slope scale depth biasing that we have that the hardware supports. When I see a hardware feature, hardware acceleration, you know I want to go for it, right? Now the problem is that in our current setup here, we are using for the shadow map, the value that we're using in the shadow map is not the render depth, it is the point-to-point distance. So because of that, we're not using the depth. It's not going to pass through the same rasterizer path that it usually does when you render, right? So since it's not passing through the rasterizer path, the standard depth path, we can't use that slope scale depth biasing. We're passing in the position as a vertex attribute that gets interpolated, and we're calculating the distance in the pixel shader, which is after the place where the slope scale depth biasing gets calculated. So we can't use that, but we want to use that. So what is a Chili to do? Well, I came up with a super crazy, dumb, crazy idea. This is so dumb that it might work idea. So what we're doing is we got the X, Y, Z, three-dimensional point coordinates, I believe, in the view space. Doesn't really matter. And we're passing that to the pixel shader. It gets interpolated during rasterization. And then in the pixel shader, we're going to do, length of X, Y, Z. And that is going to be rendered to the render target in the red as the depth. Render target dot, R32. 32-bit value in the render target as the depth. And then we're going to use that when we do our rendering, the good stuff, shadow map stuff. You know the story. All right. So what has Chili got in mind? Well, what Chili wants to do here, here's Chili's crazy idea. So I want in the SV position, we're going to put in W in here. And we're going to enable slope scale depth biasing. So this W is going to get its slope scale depth biasing, dB, processing happening to it. And this thing will be the slope scale depth bias W. Now, what is that going to do? We can't use this, right? We're using this one to render to our shadow buffer, whatever you want to call it, shadow map. That's what it's called. So what are we going to do with this? Well, here's my dumb idea. It's super dumb. So you've got the W here, and it's going to have some biasing applied to it based on the scale of the geometry relative to the camera, the slope of the geometry. Now, we're going to take another, this is SV position. This is the W coordinate of SV position. We're going to take another just standard vertex attribute, and we're going to put W, the same value in there, and we're going to interpolate it, and we're going to do the same things that you would normally have happen to it, the perspective divide, but we're not. It's not going to get slope scale depth biased because that only happens to SV position W. It's hard coded. So this one is what you would expect without bias. And this one is biased. And what we're going to do is we are going to basically compare these two values and see how much bias was applied to the value that wouldn't have been biased. This is the unadulterated. How much is this one changed? In what direction? What's the scale? What's the offset or whatever? there's going to be some relationship between these two. We want to find how much it's been biased, and then we're going to use that value to apply a similar amount of bias to here. So we're going to pass this depth in twice, figure out what work was done by the fixed hardware for depth biasing, slope scale depth biasing, and then use that change to apply a similar kind of bias to our length shadow map depth. It's pretty dumb. It's pretty crazy. This is so dumb, it might just work. So let's try it out. So what I want to do now is I want to figure out what are the numbers? What does this look like? What is the relationship between these two and this one? So what I really want to do is I want to be able to dump to a numpy and then open that up in Python. Do lots of different transformations to it. Do lots of different analyses. But right now, my numpy dumpy only works for a depth buffer. So I've got to get it to work with a render target. So similar to what I did down here, first thing I'm going to do is I'm going to factor out stuff that could be useful to both my surface dump and my numpy dump. And so that's called make staging. This is the thing that makes the staging texture that is then used to dump. So we factor that out into its own function, make staging. And then toSurface here is going to call make staging as its first line of attack here. So there you go. There you have it. Now it doesn't change anything. It just refactored the existing code, same functionality. Now we want to be able to render. Now we want to be able to dump. We want to be able to dumpy is what I'm trying to say. So I add another function, dumpy. Dumpy is obviously going to do your standard make staging. And then it's pretty much the same stuff as we saw for the depth. So this is the same idea. Numpy save. What we're doing here is we're taking in this input buffer, which, might have padding bytes at the end of every line and so forth. And we're just putting that into one contiguous vector down here, flattened to vector. And then we call numpy save. Very simple. I mentioned this in the previous video, but I was casting this to pixel and it didn't make any sense since it was a float. And then I was casting it to float in here. So I just cast it to float directly, and then we don't have to cast in here. It's much nicer. So that's just a little bit of making the code cleaner in the depth stencil dumping. But now we have the ability, we have the technology to dump a render target. So the next step is obviously now we want to dump it. We want to test out, see if it works. So we're going to dump our shadow map to a numpy file. And in doing this testing, I've realized that there were some things missing from the code. So I added in, getting info about the stencil view. And that is basically used to determine whether we are going to be copying staging from a texture in a texture array or copying from a single resource. So this case is going to be used generally when we have, cube type textures. Now in shadow mapping pass, we have to actually enable the mechanism for dumping. So I have a flag, dump flag. When you call dump shadow map, it just sets this flag to true. That's it. It even ignores the path. I just hard coded the path because this was basically just a test. And then during the execution step, this is where the dumping happens. So we do our rendering as usual to each of the 6 faces. And for each of these faces, we dumpy. And this is why I couldn't do the dump in here, because we can't dump after execution has been done. You'll overwrite all of your depth buffers. And then in execute here, this is where the dumping actually happens. We're looping through all 6 faces. We're going to render the scene from all the different points of view of the light. And for each one of those, we check the dump flag. And if it's set, we also dump that face to a numpy file, numbered based on this index here. And then after that, we set the dump flag to false again. Now, for the shadow vertex shader, what am I doing here? So I'm outputting X, Y, and Z as usual, but for W, I'm setting that as the output position Z divided by W. So my idea of this is going to be the depth value, and it should get, modified by the slope scale depth biasing. We're not doing slope scale depth biasing yet. This is just a test. But yeah, it's actually Z divided by W, not W like I said in here. But anyways, so we're now outputting that in W. And then in the pixel shader, I'm not even using that W, by the way. So I'm taking in the SV position, which should be the screen X and the screen Y in NDC coordinates. And then the Z should be, you know, in the projected Z between 0 and 1 or whatever. And then here is the view position. But we're not using the view position. I'm outputting the Z here to test, and I'm outputting just a 5.0, just a constant value. So I'm going to have this two-component output, and that's what I want to look at in numpy to see if I can, you know, get that to work. So you see here for the depth cube, I create a cube target texture, and the format is now R32G32. All right, so here we are in Git. Here's our scene. I'm going to dump the cube map. And then if we look in Git, we will see 6 boys, 6 numpy boys in our changes here. Okay, so now it's time to load this up into a Python program and see if it's actually what we would expect it to be. So I'm going to go into dumps here, and I'm going to move that, I believe, into this. Which folder should it be? It should be that folder. Okay, so we're going to move it into this one. And okay. Shadow map. Shadow. Okay, well, fine. That's fair. I'm just going to... Yes. Okay, now we're going to run this. Too many values to unpack expected to. All right. I mean, that's fair enough because this vector has 2 values for every position in the 2D array. So this isn't going to work. Basically, what we want to do is we want to pull out one or the other of those values, the R or the G. So I believe I can do that like this, taking all of the width and the height, but only taking one of the channels. And let's try it again. There you go. So here is our scene in all of its glory. Yeah, there's the sky. All right, well, it looks fairly okay. This looks, you know, within the range of what we would expect. We got values close to 1. We got values 0. Still don't know why this one is 0. I'm just thinking about it here, and I think farther away values should be larger number. This is point 992, 969. Yeah, it gets larger as you get farther away, but then this one is 0. I don't know. Maybe it has to do with the cube map that we're doing. I can't remember. It doesn't matter. It doesn't matter for this case. That's not important, probably. What is important is that that looks okay. Now let's take a look at the second component in here. That should all be 0.005 or something. 5. Yeah, it's just 5. Anywhere you look, it's 5. And that is what we output. That's what we made our shader output. So, that's beautiful. Things are so far so good. Now let's try our dumb idea of, you know, outputting 2 different streams of depth. One slope scale depth bias, the other one unadulterated, and using that as a probe to see what the slope scale depth bias circuitry will do, and then try to do that similar operation on the distance depth. So in this next commit here, we are modifying the shadow pixel shader slightly. Instead of outputting constant value of 5, we're now outputting view position .w. So let me just recap here because I probably didn't explain it clearly a few minutes ago. But position.z, this is what is going through this is the depth that goes through the pipeline, gets the slope scale depth biasing and whatever else applied to it. This one is just a straight vertex attribute that gets interpolated. And our goal is to apply operations to this one so that it will match an unadulterated depth that goes through the rasterization pipeline. That's our goal. So in the previous commit here, what we did in the vertex shader was to store in viewPosition.w Z divided by W, because you have to do that depth division. And the reason why we're putting in a view position.w is because X, Y, and Z is already being used, but W is not being used. We don't care about the fourth parameter here. So we can reuse it as the, basically as the control. You know, like in a clinical experiment, you have the test group and the control group. Well, view position.w is the control group. And then the test group is going to have the slope scale depth bias applied to it. And then we're going to see the difference between the depth, the test group and the control group. But right now we're not doing that. So these should be equal if we're doing it correctly. And that's what we want to test. That is what we want to analyze here. So again, we're going to dump. And that should get me numpy files. I can see them appearing in the folder as we speak. Then we're going to move them into here. That should overwrite. That's fine. And now we're going to run this code here. So what does this code do? Well, it loads an array. That's fair. And then it creates a difference between the first and the second components of that array. And that's useful for us, obviously, because that is going to tell us for each pixel what is the error between what we would expect and what we actually get. What we expect is the you know, the SV position W component, the Z component, and what we actually get is in the W component of the view position. And now we're going to just do some statistical analysis on that. Tell us the maximum difference in the whole image of all pixels, the minimum, tell us the mean difference, and tell us the standard deviation of the difference. And then we're going to plot that out. We're going to plot the difference out. And so here it is. We've got the maximum difference, the minimum, and they're both really absolute value terms. They're around 10% error. That's way too big. That's a problem. That means our calculation is wrong. And I mean, if we look at it here, these ones, they look very small. Well, some of them look very small. But if we go down here, this is probably where the floor is. We can see, yep, there's decently big errors. So our calculation is no good. Why is it no good? Well, pretty much to make a long story short, as much as I would like to, we cannot divide. We cannot do the depth division in the pixel shader. We've got to do that, or not in the vertex shader. We got to do it per pixel. As far as I can tell, as far as my experimentation goes, we just have to put the straight Z, put that into view position.w, and then for every pixel we divide by the depth, which is going to be in the SV position, the W coordinate there. And if we do this, then we should get much better results. So again, we run, we dump, I should see the files, I see the files, I close this, I'm going to move into the Python folder here. Yes, overwrite, and run. Okay, so now we're looking at exactly the same. I believe I did not reset. Yeah. Probably change the branch there. Okay, let's try that again. Build, run, load the scene, dump the cube map. I see the files. I move the files. And lo and behold, drum roll. Yes, our error now is on the order of like 10 to the -7, which is pretty much where the floating point error, that's pretty much on the order of floating point error, which is what you want to see. Basically, our calculation is correct. We're just getting some problems with floating point rounding error in the operations. And you can scroll around here, pretty much anywhere you go, it's going to be a good time. There's nothing pattern that I can see in here about like these areas have more error than others. It's pretty much just random floating point error in the calculations. So that means that our math now is correct. We have one stream, the control, and another stream, the test, and right now they're both equal. Now we want to apply our operation to the test. All right, so the next stage is we're actually going to try the slope scale Cartesian trick. So in the shadow mapping pass, we restore it to just R32 for the shadow map and shadow rasterizer, giving it values for the slope, scale, depth biasing here, and uncommenting it, commenting out the standard rasterizer. I adjust the point light here because every time I do my testing and stuff, I tend to make it brighter. So I might as well might as well just make it bright by default here, since that's what I'm always using. And in the shadow pixel shader, here's where the magic is going to happen. We're going to say our bias is going to be a small amount of bias here, plus the difference between the slope scaled Z and the control Z. So this amount here gets scaled by this scaling factor here, basically. And we add to that a small constant bias, and then that is going to be added to our length depth. And here it is. Here is our boy with his slope scaled. Okay, so far, this looks okay. What else have we got here? This looks sort of okay. We got some shadow here, but this looks weird. This looks wrong. I'm going to call it that is bad and wrong and dumb. The ivy looks like it's getting good shadows on the pillars, so that's okay. What else? This looks fine. This looks okay. Well, I mean, this is obviously very bad. This is terrible, right? Let's look here. And we still got our banding. So, let me just tell you guys that it was at this point that I said, this is probably not going to work. You know, it was an interesting idea to basically probe into the effect that the slope scaled fixed function hardware acceleration would do, probe that, and then try to apply that to our distance based shadow map. But these preliminary results basically tore all my hopes and crapped them out the toilet. So the question is, where do we go from here?